close to 12:10.
Yes, yes.
Yeah, Virup, you wanted to say something?
No, ma'am, I said okay.
Okay. Yeah, wait, let me. There'll be quite a lot of background noise today. Anyway, can't be avoided.
Ma'am, you can use the headphone, ma'am. That will reduce the noise.
I know, but using the headphone is kind of disturbing for me, so you'll have to bear up with the noise. Anyway, I think my voice is clearly audible. That should not be a problem, right? Is it a problem?
No, ma'am.
No, ma'am.
Yeah, because I'm close enough to the mic. Yeah. Now, so as we were discussing yesterday, so yesterday we looked at the nodal analysis and the mesh analysis. So this is what we were talking about. So nodal and mesh analysis, we looked at those two techniques. And today I'm moving on into the other circuit theorems. So before I move on to the next part, let's just revisit linearity superposition. So linear elements, actually whatever we are dealing with, I mentioned yesterday itself that mostly what we do is that we hold on to the understanding that several of the elements or several behaviors that we analyze or study, particularly from the engineering point of view, that is from the applications point of view, we assume that linearity holds either over a large range of values of the variables, or at least over small local ranges about the operating point, as we call it. Okay. So even here, when in circuit theory, whatever you'll be studying in circuit theory, we'll primarily be talking about linear elements itself. We will not be talking about any non-linear element per se. So linear elements, what does it mean? We are mainly we are talking about the passive elements, not the active elements. So passive elements that have a linear voltage current relationship. Okay. Why are we not talking about an active element here? Can you tell me anything? Why would it not? Why is it specifically mentioned passive element? You see here, it's mentioned passive element that has a linear voltage current relationship. So why passive? Why can't we just have said any electrical element? Can anybody tell me that? Which are the active elements?
Diode.
Diode is an active element. Yeah, okay. What are the other general active elements? Diode is a more specific.
Battery.
Huh? Battery. What is the general term for that? Yeah.
Voltage source.
Voltage source, and the other one would be
Current source.
Current source. So voltage sources and current sources are the two clear active elements, and diode would, again, diode or battery would be part of the voltage source. Or if you're looking at the reverse biased region, then it would be the active source. The current source for a avalanche diode. Okay. Now, so if it's a voltage or a current source that we are looking at, then why can we call it an active? Can we call it a linear element, or can we not? Why so?
Could you repeat the question? Yes.
If we are talking about voltage sources or current sources, can we talk of those being linear elements? Yes
There is
or no? Why so?
Ma'am,
Yeah.
there is no voltage current relationship in any active elements per se, so we can't really define them as linear elements.
Yeah, a little bit more specific. Say you have a voltage source.
And there is no linear relationship between voltage and current.
But what is the kind of relationship that you have?
Constant.
Constant what? Voltage source constant?
voltage source constant or current source constant, there won't be any linear relationship.
Yeah, like see, what I was targeting you.
Ma'am, ideal cases
But
voltage.
constant is also linear, na?
Okay, something more? Let's hear this one out. Yeah, Rajdeep, you were saying something. I heard Arijit's comments. Yeah.
And is it something for the voltage sources resistance being internal resistance being 0 and current
No,
sources
not
being
really.
infinite?
Not really. Not really. Yeah, Arijit's comment is actually kind of relevant. Shudha Shattu or Anindita or Gulshan, you were telling correct, but I'm kind of trying to lead you into something more.
Ma'am, voltage for voltage source doesn't change with time. Similarly for current source.
Okay, so that doesn't change with time. This has nothing to do with a linear relationship. A linear relationship does not say that the voltage or the current will change with time.
Ma'am, in case of a voltage source like a battery, no matter how much amount of current is passing through it, the voltage will always be constant.
Exactly. That is the point on it. You've got it on there. And Arijit, that is the reply also. That is that for a voltage source, you have a fixed output voltage irrespective of the amount of current that is being passed. That is the understanding of an ideal voltage source. That irrespective of the amount of current that is drawn from the voltage source, the amount of voltage that is present across the terminals would still remain the same. So that is not a linear relationship. Agreed, Arijit?
Yes, ma'am.
Okay. So that is the point. And Arnika, I suppose you got it that why it's not just the variation with time. Time has
Yes,
nothing to
ma'am.
do with the linearity.
Yes, ma'am.
Okay. And the others, I hope, got this point. So, which is why the simple thing, this simple definition when you're talking about it, it's a passive element that has a linear voltage current relationship. Please note the words which are being mentioned, So, why is it a passive? These should be questions that you should be raising to yourself. I have just copied from the book. Okay. And I copied it out here. But when I'm telling to you, then it's a question that strikes to me and myself that, okay, why is it only a passive element? Why not an active element? And therein stands the answer that do I have a linear voltage current relation? No, I don't. Why so? Because the voltage for a voltage source, voltage is fixed, current could be any which value. Similarly, for a current source, current would be fixed, voltage could be any which value. So naturally, it's not a linear relationship then. Okay. Now, coming back to this one. So linearity, when I say an element is linear, that means it must satisfy two principles. Although I did mention here this way, but I went into a bit more of mathematics here. So there are the two principles here. First is that of homogeneity, and the other is that of superposition. Homogeneity, mathematically, what does it say? Like if you've got A into B is equal to AB. Okay. Yeah, I think you can get it. In case you find it a problem understanding this one, please let me know. I'll move on into a board and start writing them. Okay. So if A into B is equal to AB, then A into K times of B would ensure that you would have K times of this product AB. So this is homogeneity. Okay. This is homogeneity. While for superposition, the rule says if you've got A plus B, so individual A and individual B, okay. But if you've got alpha times of A plus B, it is equivalent to alpha times of A added to alpha times of B. We take these for granted, but there's a lot of importance and practical significance in these two. Okay. Or if you write it mathematically, like let me kind of just outline this one out a bit. This particular expression, okay. I don't know whether I'll get it straight out. So, yeah. I've written it one shot here because it's in my note. So usually what would happen is I'll just write it out here on top itself. So supposing you've got say you've got x1 and x2 are two input variables, and you've got defined outputs fx1 and fx2. So x1 maps to fx1, and similarly x2 maps to fx2. That's the understanding. Okay, so it's a function or a mapping, mathematically speaking. Fine. So this is from the input set, this is the output set, corresponding outputs. So you have a clear relation or a mapping between them. Now, if that is so, then I can define x1 plus x2, that in the output part, so that should generate a function operating on x1 plus x2 should generate f of x1 plus x2. That's the understanding. Now, so if I have the input a1 x1 plus a2 x2, this particular input, this particular input a1 x1 plus a2 x2. So where does that port to in the output? That will be function of a1 x1 plus a2 x2. Now, using these two principles, what happens is f of a1 x1 plus of a2 x2, if you applied superposition first, this principle first, so what would that give you? Anybody tell me? I'm asking for the interim step, basically.
f of ax1 plus f of ax2.
Right. F of a1 x1 plus of f of a2 x2. Right? Okay. So this is superposition. And then f of a1 x1. F of x1 gives you f of x1. Okay. By the way, this is also f and this is also f. I hope you are the script x f and this kind of this discrete f. So f of a1 x1, you would apply homogeneity here, and that would give you a1 times of please go ahead.
f of x1 plus a2 times f of x2.
Right. Yeah. In fact, if you are giving me such like smooth answers, it's lovely for me. I also get enthusiasm that my students are in the class responding. So that's good for me. So you land up at this one. So although we just simply take it for granted that this holds, but it is actually two particular rules, one applied after the other. And please note that here you can't apply homogeneity first. How will you do so? Because it's not the same constant multiplying both of these. So you have to go superposition and then homogeneity. Okay, so that is the order in which you have to apply these two principles, mathematically speaking. Now, linear, this is a linear map or a linear function or a linear system, but this equation, y is equal to mx plus c. What is this? Equation of?
Equation of a straight line.
Straight line passing through the origin.
But equation of a straight line is
Slope
not
form.
linear.
Slope
Then
form.
with see the intercept.
Yes, because of the presence of this intercept. So equation of a straight line is not linear. Please understand that. Okay. So we call this actually affine. This is an affine relation, but it is not a linear relation. Mathematically speaking, equation of a straight line is an affine relation. AFFINE. Okay. It is not linear. Please stay clear about that. And you are absolutely right. It is violated because of the presence of this intercept. So what would be a equivalent linear relation from this equation of a straight line? How could you get that? Anybody?
Y equal to mx.
No. Y is equal to mx. You're forgetting the c. You can't forget the c.
Okay.
So what can you do? What kind of a change if you did or something? Some manipulation which would give you a linear relation from this one. How could you do this?
We
Yeah.
can write it in slope intercept form.
Kind of. Actually, if you look at the small changes. What is delta y?
M delta x.
M delta x.
M?
M delta x.
M delta x. Now see, this one is linear. Get it? So this is the equation of a straight line, which is an affine relation. But in terms of the changes in y, that is related linearly to the changes in x. Okay, because that gets rid of your intercept. So these are small things that you can. The reason why I'm pointing out this one is something which might apparently look non-linear to you, or not linear rather to you. You can manipulate it so that you get to a part which becomes linear. And this is linear in the small changes. It is linear in the changes. It is not linear in the actual variable, but it is linear in the changes. And we make use of this kind of principles in order to look at sensing principles. Actually, if you look at, if you've looked at fundamental of instrumentation, so they're capacitive sensors. So you are currently doing that. So capacitive sensors, when you look at that, in order to get a linear relation in a capacitive sensor, you use a principle something like this. Okay. Now, so that is about the homogeneity and superposition overall. Now coming down to a little bit more details about this. So how can you apply that? What is happening? So the homogeneity part. So if you're looking at the homogeneity part, homogeneity means this equation. So linear current voltage relation, that a typical example would be if you have a linear current voltage relation. So what would that imply? That a multiplication of a time invariant or a time varying current through the element by a constant k results in the multiplication of the corresponding voltage across the element also by the same constant k. Written it is so much. Expressed it would be simply that V is equal to IR. So k times of I times R would give you k times of V. The same constant. Okay. This is just what I mean by all this much of writing. Small v and small I means they are time varying currents and voltages, instantaneous voltages and currents. Okay. So this is what you get. So this goodness in all of the linear elements, and linear elements are all of the passive elements. That means resistance, inductance, capacitance. Then you have the mutually coupled inductors. So those are also linear elements. Okay. So for each of them, this kind of a goodness holds. In the sense of some variable or the other, you can express it as a linear change. Okay. And that, what is the practical significance of that? Scaling. Or scaled models. Okay. What does that mean? That supposing you want to make some simulation, rather some hardware model of a large plant or something. So if you want to typical process for designing a large any plant would be to first simulate it. Software simulation would be done. Then part by part you would put in hardware, small hardware into that. Okay, and check that. That is called hardware in loop simulation. And then you would make a scaled down model of that whole plant. Say 1:10 ratio or 1:100 ratio or whatever. So you would have a scaled down model. So that particular ratio, that is essentially this. Okay, and you have the understanding that how would that scaled down model, how would the elements, how would you choose the elements in that scaled down model would depend upon these kind of relations. What is the relation between the variables at each and every, across each and every element or in each and every element that you're choosing in that particular plant. So depending upon that, you would choose that, assuming that the elements are behaving linearly. So that is how you would do it. And what do I mean by saying how you're doing so? Like, for example, if you're here, you're thinking of V is equal to I times of R. But if you are deriving I is equal to, it would be 1 by R times of V. Okay. So if I had that, so that the scaling factor would be K by R in that 1 by K times of R instead of a K times of R. So it would be a 1 by K factor scaling instead of a K times scaling. Here it would as it be a K times scaling. But in that kind of a relation, it might be a 1 by K times scaling. So those things would be there. How is the relation? Depending upon that, you can do a scaling of that. That is the importance of homogeneity. What about superposition? Superposition is simply this one mathematically, that alpha times of A plus B is equal to alpha B plus of alpha B. That means the response at any point in the linear circuit, let me go back to this one. So the response at any point in the linear circuit having more than one independent source can be obtained as a sum of the responses caused by each independent source. So caused by each independent source acting alone. Okay, so it's the sum of the responses due to each independent source. That means if you've got one source V1 and the other source, one source V1 and the other source V2, for the source V1, you have a response Ri1. For the source V2, you have some response Ri2. Okay, and you can combine these two as the net effect. Right? So what does that say? That if you need to augment, which is exactly the principle when we use batteries. So you need a 6-volt supply, you put in one battery. You need 12-volt supply, you put in 2 batteries in parallel. Sorry, in series. Okay, and so on and so forth. So how can you do that? Because this holds, this superposition holds. Okay, you can disregard the effect of this one. There will be other examples also where we will be using the superposition theorem. So the superposition theorem is there where we look at the effects. We can analyze the circuit also in terms of the effects of each of the individual sources and then the combined effect due to all of these sources. That is possible. That means that the effect of one is linearly linear. The effects of each of those can be added in separately. If it's non-linear, then you have no such guarantee. Please understand that. Okay, that you put on one particular source and then you switch on the other source that interacts non-linearly with the first source. As a result, the net effect is not just a mere sum total. It could be some other effect. Okay. That's what actually happens in the understanding of a subject. So it would be good if you had a linearity principle, that you attend one class, whatever you understand from that is independent from your learning from the other next class. So even if you miss 5 classes in between, you simply go on accumulating whatever you've learned in each of the separate classes and then bunch them together. But sadly enough, what happens is it's a non-linear effect. So what you learned the previous day, that kind of interacts with what you're learning today and gives you a non-linear effect. Only then can you learn, if you've learned from what you've done the previous day. These are not linearly separable. Just simple superposition does not hold. Okay?
Yes.
Now, yeah, I've already mentioned this one. Now for the dependent sources. For the dependent sources also you can mention linear dependent sources, or you can have linear dependent sources, meaning that dependent current or voltage sources whose output currents or voltages, this is O/P is output and I/P is input. I standardly use these notations. Okay, so whose output current or voltage is proportional only to the first power of some current or voltage variable in the circuit, or to the sum of such quantities. Sum is allowable. It's a linear, so superposition will hold. So sum of such quantities is allowable. What do we mean by that? That if we have some voltage source, dependent voltage source, dependent on some I1 and some V2 in this particular form, 0.6 I1 minus 14 times V2, so that is a linear source. Why so? Because if we have these multiplied by alpha, each of these two multiplied by alpha, it is equivalently this whole thing multiplied by alpha, alpha times of Vs. So it's a linear relation. So it's a linear dependent source. However, if you have, obviously, if you have something like this, Vs is equal to 0.6 I1 square. So naturally, if you have I1 multiplied by an alpha, it does not work out to be alpha Vs. Neither is a product. Any product form also violates the linearity principle. Okay. So this is just kind of to show that one. Yeah. So if you are talking of a linear circuit, please understand independent sources are out of the paradigm of linear elements, as we've discussed earlier. So it's a circuit composed entirely of, I'm sorry, this is independent sources. You can just look it up in the book. So circuit composed entirely of independent sources, linear dependent sources, and linear elements. So these two, the dependent sources as well as the passive elements, must be linear. Along with that, you could have independent sources. And any circuit which has these kind of elements would be called a linear circuit. Okay. Now for the superposition theorem. The superposition theorem, if you read it, this is how it goes. In any linear resistive network, why resistive? Because right now we are just dealing with resistive networks. We can have superposition actually for any linear network per se. Okay. So in any linear resistive networks, I'll just mark this out that it's kind of an optional here. It is just because we are dealing with resistive that we've got it marked out. Else not very significant. Okay. Yeah. So in any linear network containing several sources, the voltage across or the current through, since we are considering the resistive, so any resistor or the source may be calculated by adding algebraically all the individual voltages or currents caused by each independent source acting alone. So this is caused by each independent source acting alone, with all the other independent voltage sources. So voltage sources are replaced by short circuits, while current sources are replaced by open circuits. Very simple, but still, why so? What is the logic? Hello? Hello?
And the internal resistances of the voltage source is 0 and the current source is infinity, that's why.
No, what have you done? You have replaced a voltage source by a short circuit. So what will happen?
Resistance will become 0 of that path.
So the effective voltage drop, what will happen to that voltage drop? That will become?
0.
That will become 0. So you want to kill that voltage source. Okay. In the book, actually, you'll find a very, I love this work actually, though I have not mentioned it here. They clearly say kill sources. So the objective is to kill the sources. Okay. So if you want to kill a source, you want to kill a voltage source. That means whatever is the voltage drop supplied by it, voltage across the terminal supplied by it, you want to pull it down to 0. So what do you have to do? You have to short it. Similarly, killing a current source would mean?
Open circuit.
So that there is no current flowing through that particular branch. Okay. Short circuit would be exactly the opposite thing that you would do for a current source. Please understand. Similarly, so for a voltage source. Well, voltage source, if you replace by an open circuit, the whole voltage would get dropped across that. There would be no current flow, so no voltage to be transferred elsewhere in the circuit. Okay. So you are killing sources in order to kill the other sources. This is for all the other. Let me highlight out the other. Otherwise, you start killing the major itself. It is for the others that you are looking at. So you are studying the effect due to each independent source by killing the other sources. So this is the kill part. Okay. So kill the other sources. Right? And that means that you replace the voltage sources by shorts and the current sources by open circuits. Is this clear to everybody? Any confusion?
Can you please show an example of this one? Like it's
Of course,
clear to me.
of course, I will be. I'm reading out all these languages. See, in this particular part, I will be reading out long paragraphs like this because you need to know the language of it. But stay assured that I'll be showing you examples so that you get familiar with what's happening. Okay?
Okay, ma'am.
Yeah. And here is the first example coming up. So here, if you've got it, so what are we doing? We are looking at sources which act as, here you've got two current sources. So these act as forcing functions. Mathematically speaking, you have got forcing functions or zero input responses or the homogeneous responses and responses of the system. You know, mathematically, that's what you do for differential equations, right? Okay. So the voltage is produced in this case, this V1, V2 that we are going to analyze. These are going to be the response functions, while the sources are nothing but the forcing functions. You've got two current sources here. So if you thought of a KCL, let's do a nodal. So this would be reference, as you understand, though it's not marked here. Let me mark it. This is reference. Yeah. So if you're looking at the KCL at node 1, so I've got it listed here, so I'm leaving it as this. Actually, in the sense that we've gone about this way. Would anybody want to speak out? It's not given in exactly that order. Anybody wants to quickly speak it out? Not really. Okay. So there is a minus of IA plus of 5 times of V1 minus V2 by 5 plus of V1 by 2 would be equal to 0. And that, if you expressed it, it would be this one. Okay. And so you would have this. And for IB, this particular part, if you started from here, it would be V2 minus V1 by 5 minus of IB, current entering, plus of V2 by 1 would be equal to 0. And you would land up at this particular equation. V2 by 1. Oh, acha, you had V2 by 5 here. So that gives you the 1.2. Yeah. And this minus 0.2 of V1. So these are the two relations for IA and IB and the corresponding V1 and V2. So if you, supposing you use one value of IA and one value of IB at a particular, for a particular duration, you call them IAX, IBX. Corresponding, the voltages would be V1X and V2X. Then after a certain duration, you change the supply to a IAY and a IBY. Then the corresponding voltages would be V1Y and V2Y. Okay. Then if you were to apply a combined IAX plus of IAY and a IBX plus of IBY, you would be assured of having a combined response V1X plus of V1Y and V2X plus of V2Y. This would be assured for you by means of superposition theorem. Okay. So what I'm saying is that supposing it could be anything actually. Say your profiles for, this is with time, and say this is your profile for IA and this is your profile for IB. Supposing you've got
X and Y are different instances of time.
no, just different levels. I'm showing you. Assume these are constant values. Even if they were not, it would not matter, okay? Since these are just two values specifically mentioned, so which is why I've taken two different levels. Say this one is your IAX, this one is your IAY, this one is IBX, this one is IBY. Okay? Some values of IA and IB. So till this duration of time, say you had is the same duration of time. Till this duration of time, assume that you had IAX and IBX for which you were testing the system. you would get some output V1x and V2x. It's a fixed value for which you are solving it. Instantaneous value is the same. My God, that was a queer laughter from somebody. Please refrain from such laughters in the class. Yeah. So is this clear? Or do you want me to write out separately?
Ma'am,
Hello?
why would we want to add them?
Add them. I'll come to that later. As for now, if you had something like this and something like this, so you would have a corresponding V1x and a V2x. Is this much clear?
Yes.
Okay. Then, supposing beyond a certain duration, this value of IA changed to IAY, while the value of IB changed to some IBY. Then the responses would change to a V1Y and a V2Y. Is this much also clear?
Yes, ma'am.
Okay. Now, the question you're asking is why would you have a combination of this? Okay. This is a scenario where you can think of, now supposing you have got, supposing these are the levels of changes that you're allowed in IA and IB. And supposing it's a generating some transformer output point where you've got to supply a certain amount of current, okay, from one transformer, transformer 1, and from transformer 2. And you know that you require a certain amount of V1 or a certain amount of V2. So depending upon the load that is connected, say one of these is the loads, either this or any of these is a load. So depending upon the load that has to be catered to, you have to play around with the values that you can supply from IA and IB, either this much or some combination, some linear combination of these. Because these are the only two discrete values that you're allowed to supply, or some linear combination. You're not allowed values which you can supply intermediate. Okay, so then that linear combination, you could work out at any linear combination. You could, I could put in some alpha times of IX plus some beta times of IY. So I would again be assured of an alpha times of this plus a beta times of this. Similarly, an alpha times of this plus a beta times of this. Right? Similarly, so for this one. Do you get it? Hello?
No, ma'am.
If you are supplying, supposing it's a, oh, actually you've not studied TTL gates and so on and so forth.
Ma'am, one question. What is this we are studying? I am unable to get the idea of this. Why are we changing the sources to IAX and all? Superposition. Okay.
This is superposition theorem. Okay, and supposing you have a scenario where you know that what would happen if you supplied IAX or you supplied some other value, IAY. How would that change the response? So if you have some combination, some pair IAX, IBX, you would have the output responses V1X, V2X. If you had some other pair IAY, IBY, you would have some corresponding responses V1Y, V2Y. Okay. If you had some linear combination of these in the supply, then you would be assured of a linear combination corresponding in the responses also. That is all that we are talking about. Okay, because you have this particular relations. These two relations are as such independent of each other, because this is for the KCL at 1, this is for the KCL at 2. So IA, how is it related to V1 and V2? That is one relation. And IB, how is it related to V1 and V2, the two responses? That is the other relation. So you can even treat these independently. It does not say that if you've got some factor of IA, some K times of IA, then you have to have a K times of IB also. No, that's not necessary. You can have a K dash times of IB. Okay, so if there are two transformers which are supplying, say it's any power station that you've got the different transformers on. Okay, so depending upon the load that has to be catered to, say during the early morning, during the daytime, during some kind of a lockdown or a strike, or during some kind of peak hours, or in the evenings when it's kind of slightly going down, summer or winter, so the effects of ACs, etc. coming in, okay, factories on and so on. So night shift coming in the factories and so on. So depending upon that, what are the values to be supplied by these to maintain the voltages at the different respective supply points, rather the client points, that you could fix independently, assuming that linearity holds. That is the whole point. As long as you knew the independent relation of IA and how it affects the V1 and the V2. We've taken a simple circuit where this just two supply points. Okay?
Ma'am, as we have already learned the superposition principle, which is basically used for calculating the current through a given branch. So is it related to that in some way?
Superposition is only used to calculate current through a limited branch. Why so?
Ma'am, we have learned that because we ignore all other voltage sources and we consider only one voltage source, and we find out the current.
There is nothing which says it has to be a voltage source. There is nothing which says it has to be a current source. There is nothing which says it has to be all voltage sources. There is nothing which says it has to be all current sources. It could be anything. Get back to this definition. In any linear resistive network, we are considering resistive as of now. So in any linear passive network, considering several sources, it could be several sources, the voltage across or the current through any of those passive elements or source may be calculated by adding algebraically all the individual voltages or currents caused by each independent source acting alone, while you are killing all the other sources.
Okay.
That is superposition theorem. Okay. So in this particular case study that we've seen, we have got two current sources and we are evaluating for the responses for two voltages. I'll show you other examples where we'll do something different. Okay. So let's move on to the next one.
Ma'am, we basically know the voltages of V1 and V2 for IA and IB respectively, right?
Yeah.
Ma'am, so
you have a relation for these. You have a relation for these.
Yes, ma'am. So shouldn't we write V1 and V2 in terms of IA and IB and not the other way around?
Yes, you can. Now the point is that here the objective when they're looking at this one is that you can treat, as I said, if it's a transformer supplying, depends on which you're interested in looking at. If you're interested, if you are thinking of the power to be consumed at a particular factory, that will be a V1. At some particular outlet in the factory, that will be V1. And some other factory or some other outlet in the factory, that will be a V2. Then you would write V1 or V2 in terms of the IA and IB. If you're thinking from the transformer, the production point of view, you have to supply a V1 and V2 to the customer. You would think in terms of the IA or the IB, that how many transformers do I need to keep up? If so, each of those transformers, how much is the load distribution? How would I distribute the load in the two transformers? How so? How can I combine them in order to supply, or how can I augment? If I were to augment those in stages, then what would be the effect on this V1 and V2? If I'm changing this
Okay,
one,
ma'am. Okay, ma'am. I got it, ma'am.
okay, so that decides. Okay, coming on to two other examples. So here you've got a voltage source, you've got a current source. Okay, and suppose, as per what you mentioned earlier, whoever was mentioning, that we are interested in finding out Ix here. Say we are interested in finding out Ix or the voltage at this particular node V. The voltage at this particular node V or the Ix current through this 9 ohms branch. So using superposition theorem, what would happen is that you would take the effect of one source, kill the other. Killing this one means it's killing a current source, so it's open circuit. If you're open circuiting it, that means this is going to supply just in this particular loop itself. So what is the current through this one? Current through this one is nothing, just current division. So it is 3 by 15. Sorry, not even current division, my bad. So this is just simply the current through this particular loop. So it is 3 by 6 plus of 9, that's 15. So you have 0.2 amperes. So this is the due to the 3 volt voltage source. Now, how much is Ix? Actually, let me write it off. I should have written an Ix dashed and Ix double dashed. So this is an Ix dashed, and this should be an Ix double dashed. And total Ix, this would be actually equal to Ix dashed plus of Ix double dashed. Right. Yeah. So this would be it. So this would be a Ix dashed would be this one. Then for the next one, this one, you want to kill the voltage source. Killing a voltage source means short this one. So if you are shorting this one, then current through this branch. So current division now. So 6 by, naturally in the reverse order, so 6 by 6 plus 9, 15 of 2 amperes. So that is your 0.8 amperes. So total current will be due to the effects of these individual sources, total Ix would be this plus this, that is equal to 1 amperes. Okay. This is solving for Ix using the superposition method. You've already learned the mesh analysis as well as the nodal analysis. Okay. So let's look at the nodal analysis here. So for the nodal analysis, naturally just solving for this particular node, taking this as the reference, would do the job. No point solving it for this particular node. You already know the value and we are not interested. We are interested in just finding out this one. So if you take the nodal equation just at this point, so what do you end up with? So this would be V minus of a 3 by 6, and this is current entering, so minus of 2 plus of V by 9 is equal to 0. And if you rearrange it, it is this one. So V would be equal to 9 volts. V is equal to 9 volts, and so naturally Ix is equal to V by 9. So that is equal to 1 amperes. So this would be the, if you were solving it using the nodal. If you were to solve it using the mesh, yeah.
Nothing.
Okay. If you want to solve it using the mesh, then in that particular case, it's obvious that this mesh, there is nothing to work out on because there's a current source. So it's going to be a super mesh kind of a thing. So this is Is of 2 amperes is already known. So just solving for this particular mesh, and this is the current I. So it is minus 3 plus of 6 times of I plus of 9 times of I. And this direction is already in this sense. So it is I plus of 2 amp, right? So this is the particular equation. This is equal to 0. And if you solve it, so your I comes out to be minus 1 actually. So actually, so your I of X comes out to be 2 plus of I. So that is nothing but 1 amperes. And so please understand what's happening. So this Is actually supplies 1 amperes through this one, and another 1 amperes goes through this one. So that is what actually happens if you look at this one. So that gives you additionally that information. However, this is applying source transformation, applying superposition theorem, this is how you would solve it. Okay, so I've just shown you that you could have done the same thing using either the nodal method or using the mesh method also. It is conversant to, it is good to remain conversant with each of the different methods. That's the whole principle of, a whole objective of this particular chapter. And you do good to know all the techniques so that you can apply any which of that as required. Now, if you apply superposition to the next circuit, this one, here you've got current sources as well as voltage sources, and you've got a dependent source also. Okay. You are trying to evaluate I of x, current through this particular branch. Now, so consider when you've got this one, if you would kill all the independent sources. There is no point in killing dependent sources. So dependent sources are anyway dependent on something else. So what's the point in killing them, right? So you can only apply the superposition till that part. So look at the effect of this one, killing this one. Killing this one means just opening it out. So that means you just have one single loop. So one single loop, so that is minus 10 plus of twice of ix plus of 1 of ix plus of twice of ix. So total 5 of ix dashed, first one, so ix dashed. So ix dashed is equal to 2 amperes. Next is for this one, you have to kill the independent source. So independent source means this one has to be killed. So this is open circuited. That means there is no current flowing through this particular branch. So you can forget this one. It is simply this one that you're thinking of. Okay. So in this particular case, oh, my mistake. Nobody pointed out also. I'm killing a voltage source. I'm killing a voltage source means I must short it, not open circuit it. So if I'm shorting this one, so naturally from this I've got a shorted part through here. This one supplying current into this one, and there's a path through this 1 ohm into this dependent voltage source, price of ix. Ix is the current marked in this particular sense. Okay, so you apply the KCL at the node 1. KCL at the node 1 would be, you have a V as we've written here. So a V by 2 or V double dashed, since it's the second one that you're looking at. So V double dashed by 2 plus of V double dash minus twice Ix double dashed by 1 minus of a 3 is equal to 0. So this branch, then this branch, then this one. Okay, if you just rearrange it, this is how you get. And the relation between Ix, how is it related? Ix double dashed is nothing but V double dashed by 2. So this is the relation. So just substitute for it there and solve it. You will get Ix double dash is equal to minus 0.6 amperes. So your overall total Ix would be Ix dash plus of Ix double dash. So that would be 1.4 amperes. Does this answer the query that, answer your confusion that superposition can be applied for currents as well as voltages and for determining whether it be independent sources or dependent sources? I'm waiting for a response. Arijit says yes, madam. Okay. Yeah. So I hope this much, till this much is clear. Now, the next point up is source, next technique up is source transformations. Source transformations, how do we think of that? And where does it actually arise from, the concept? If you had ideal sources, say we look at some IV characteristic, current voltage characteristic. If you had ideal sources, then as we discussed, it would be able to supply a fixed value of voltage irrespective of amount of current that is drawn through it. So this would be the kind of response for an ideal source. However, what happens is that if you've got a practical source, then in that case, you have a certain amount of drop that happens due to the presence. As the load increases, the amount of drop also increases. Okay, and as a result, you have a decrease in the terminal voltage of the source. So that has to be accounted for. Practical example, if you are starting an automobile with the headlights on, because you're starting it, so that starting energy that is required, that is pulled from that same source. As a result, the headlights, which is a load, resistive load, so the headlights typically are perceptibly dimmed. There's a perceptible dimming of the headlights. Okay, because you require a starter current of almost about 100 amperes. So say for this particular case itself, say that for no current flow, you had a battery terminal voltage of 12 volts. For 100 amperes during the starting, you have a battery terminal voltage of 11 volts. Say you've measured it and you found a drop of 1 volt. So naturally, in the practical voltage source, how is it appearing? A drop of 1 volt due to 100 amp being pulled. So that's actually, that gives you 12 volt in series with a internal resistance of 0.01 ohms. Okay, so the overall relation, if the circuit would look like this. So this would be the ideal source, and for the practical source, this would be, you would have resistance, internal resistance associated with the source, which would make it a practical source, and then you would have the terminal voltage here, to which you would have the particular load connected, the load current IL and the terminal voltage VL, with the load being RL, denoted as RL. So you would have this particular relation, V of L OC, open circuit, is equal to R of I, internal resistance, into I of L plus of VL. Okay, so VLOC is nothing but this itself. So VLOC minus VLOC plus of IL times of RI plus of VL is equal to 0. So that is, from there you are getting this particular relation. And for this particular case, if you put in the values, so this is what you have. Correspondingly, for the current, you would have a relation 1200 minus of 100 times of VL. So what would that say? That if your VL was 0, then the corresponding IL is 1200. So this is the short circuit current in this particular circuit. If you short this one, then the total current that would go through this particular circuit would be a maximum of 1200 amperes. Obviously, it's not to be allowed. There'll be a burnout or something. But calculated, in order to get the response, we quite often use this as a characteristic curve that is supplied, okay, for the battery or whatever we are supplying. So this would be the short circuit current, and this would be the open circuit voltage. So voltage source, we desire our open voltage, which should be the same. So this is the ideal voltage source, and this would be the relation for that particular case. Furthermore, so if you look at each and every point on this characteristic, that relates to a different value of RL. As you keep on changing the RL, so you would actually traverse from this one. So RL is equal to infinity, you would have VL equal to VLOC. RL equal to 0, you would have VL equal to 0, IL equal to ILSC, the short circuit current, and interim values, depending on that. One particular response point is very much noted and significant also. That is the point at which the load voltage is exactly half of the open circuit voltage. VL is equal to half of VLOC. Okay, what is the significance of that? RL is the same. So since VL has gone down to half, so power, that's a point where you have maximum power that is transferred. Okay, so your R of L at that particular point, if you just put VL is equal to half of VLOC in this particular relation, okay, and if you solve it for this relation, then you will find that R of L is nothing but VL into I of L. So that is equal to Ri, that is equal to 0.01 ohms. Okay, so you would get that. So the This occurs at a scenario where your internal resistance is equivalent to the, rather your load resistance matches the internal resistance of the particular source of the circuit. Now, to come on further, let us look at a general practical voltage source, and corresponding let's look at a general practical current source. So this would be the corresponding current source. Okay. This would also be VFL. This would be IFL. And this is VLOC, and this is ILS. So since it is a voltage source, ideal voltage source, so ideal voltage source would have supplied this irrespective of current drawn. Ideal current source will supply the same current irrespective of voltage requirement across the terminals. Okay, and these two are called to be dual circuits of each other. This one and this one, duals of each other. So you've got a single loop here, corresponding there's a single node pair here. Okay, you've got the same current flowing through these, you've got the same voltage dropped through across these. Okay, and so for in place of a voltage source, you've got a corresponding current source. Okay, so series circuit, corresponding parallel circuit. So these are the duals that you have. Now in the duals, if you look at this one loop equation, so VL would be equal to, I've directly written the VL equal to VS minus of RSV, because you are talking in terms of the voltage source, RSV times IFL. Correspondingly here, what would be the equation? IFL would be equal to IFS minus the drop through this one. So that is VL by R of SI. I for the current source configuration. Okay. VLOC here, if it is open circuited, this is open circuited. So VLOC would be same as VS. Okay. ILSC, if this is shorted, would be nothing but this by this. Okay. Correspondingly here, if you look at it, ILSC, if this is shorted, naturally this will be bypass. So ILSC would be nothing but IFS, and VLOC would be, this is open circuited. So this would be whatever is the drop across this one. So this would be this into this. So that would be the characteristics. So these are the characteristics of the general practical voltage source, general practical current source, and you would have the same kind of a relation apart from these two basic characteristics being different.
Could you please repeat the notations OC and LC? I'm getting confused there.
Oh, okay, let me write it down. OC is for open current, open circuit, sorry. So what is SC?
Short circuit.
Yes. Feel free to ask me these, because to me this is so obvious that I might kind of just breeze through it. But if you have any problems in these notations or whatever, feel free to ask. Anything else you wanted clarified?
No, ma'am.
Okay. These characteristics I hope are clear now to you. So these are the duals that we are talking about. Now, I will come back into this one a little later. Let me just first shift to this one first. Let me shift to equivalent sources, then I'll scroll back up and come to this one then again. So equivalent sources, we looked at that dual circuit. Now, if you are thinking of equivalent, the definition of equivalent sources, when can we say that two sources are equivalent? If they produce identical values of VL and IL. So they have to produce identical values of VL and IL when they are connected to the identical values of RL. you have the same load connected or same values of the load connected, you should get same values of the terminal voltages and currents, no matter what the value of RL may be. If you've got this one satisfied, then you can say that the sources are equivalent. Okay, that means naturally at the two extreme points also, they will provide the same open circuit voltage and the same short circuit current. And since the remainder of it is linear relations, so these are linear relations. So if you've got these two endpoints the same, then you are sure that you've got equivalent sources. Okay. And so just going by the previous two relations for the two dual parts. So from the voltage part, we got equivalent voltage source, we got VLOC was equal to the supply voltage itself. And in the current representation, current source representation, it was IS into R of S of I. For the short circuit current, this was nothing but the source current itself, current source. In the voltage source part, it was voltage source by the internal resistance, RSP. Okay. And since Vs and Is are the same, so naturally the RSI is equal to the RSV, that is equal to R of S. So it's the same R. So that gets established. That since it's an equivalent source, if you treat it, so this is the same R that you have. So accordingly, you can have source transformations which can be done. So you can represent a circuit either as a current source with a parallel resistance or as a voltage source with a series resistance. The resistance values being the same, because it's the same R that's coming up. Okay. So what this says is that if you have, practically what happens, you can measure, you have two terminals from any circuit or source point, you have two terminals which are jutting out. Across those two terminals, you affix different values of resistances, or you affix a rheostat or a potentiometer depending on how large or big the circuit is, and you keep on changing the resistance value. Okay. And depending upon that, whatever the values that you get, short circuit how much is it, open circuit how much is it, or interim whatever values how much are they, assuming linearity to hold, you can map back. So you're looking from this side, you can map back into your choice of a model, whether it's a voltage source with a series resistance, internal resistance, or you can map it equivalently as a current source with a corresponding parallel internal resistance. It is your choice as the engineer to decide upon this model or that model, if it's an unknown circuit that you're looking at. Okay. Again, from the forward point of view, when you're analyzing a circuit somewhere like this, but beyond this point, supposing you've got a parallel network or something, then instead of having just this one series branch, you can convert it into a parallel branch by doing an equivalent source transformation from this to this and having this in parallel with so on and so forth. So that allows you to go into analysis easier. Okay. And that is exactly the principle of source transformations that we will talk of. Small example here itself. Supposing you've got a circuit like this, okay, and you wanted to connect an RL to this one. So simplifying this one off, how could you look at it? So this is a series voltage source with a series resistance. You can convert it into a corresponding current source with a parallel resistance. So current source would be naturally 12 by 3. So that would be the 4 amps, and this would have the 3 in parallel to this. So it is across these two particular nodes. So we are just looking across these two particular nodes, and we are replacing the part to the left of that. We are doing a equivalent source transformation to the left of that. Cut-C superposition. Linearity rather. Just a minute. I'll just take out for 2 minutes or so. Yeah. Okay. So I hope you got a chance to look through this one a bit. So you've got this one. So that's the equivalent. So 12 volts, 3 ohms, that is the 4 amps, 3. And this is now a parallel combination. So this is a parallel combination of 3 and 6. That's nothing but 2 ohms. Okay. So now you've got this. And you've got this one, 7 ohms. So it is good to transform it back into a voltage source and a series resistance. So voltage source will be 4 into 2, 8 volts. This will be series 2 ohms. 2 plus 7 will give you 9. So this is the equivalent terminal. Across for this particular load resistance, it will view this whole circuit as equivalent. An equivalent source would be 8 volts and 9 ohms with internal resistance of 9 ohms. This is what this load sees this whole circuit as. It need not know whether all of this is there or not. It can simply treat this as a voltage source with a series internal resistance. Okay. Yeah. One more thing is that naturally these are the two problems with using source transformations. Number of transformations for a complicated circuit increase, and further on the dependent sources, it's only possible, it might not be possible in all cases also, and dependent sources, it's usually inapplicable. So you can do this only for independent sources. Continuing on further into the next theorem, that is that of the maximum power theorem. So the maximum power theorem, again the theory part of it. I hope till the source transformations, application of the source transformations, or the understanding of the source transformations, why we do that. You know the technique maybe, but the objective is to understand as to why you're doing it. At least get some basic idea where it might be applicable. I hope that's clear. Some response would be appreciated.
Yes, ma'am.
Yes, ma'am.
Yeah. Now, coming on to a maximum power, the maximum power theorem. So theory-wise, language-wise, an independent voltage source in series with a resistance Rs, or an independent current source with a resistance Rs in parallel. As you can see, this is nothing but the equivalent representations. The voltage source representation or the current source representation. This delivers a maximum power to that load resistance for which the load resistance matches the internal resistance. Okay. And theory-wise, I don't know whether you're aware of this or not, but still, just to go about it, suppose we consider a voltage source with the series resistance. You could do the same for that dual circuit also and work it equivalently. So say, suppose you've got this one. So in this, what would be the power delivered? By the way, superposition holds for voltages and currents. It does not hold for power or energy. Okay, those are products. IL into VL, products, or integral dt. So superposition does not hold there. Just as we saw that superposition does not hold for any dependent source, which is a multiplicative of 2 IVs or something. So that same thing would apply. Now, so the power, as you see, it is nothing but, I've just expressed it in terms of the I itself. So IL square of RL. So IL in this one, what would it be? It would be nothing but Vs by Rs plus RL. That would be the IL. So just substituting that here, whole square RL. So you would have this whole expression. Further on, to find out the maximum, when would you have maximum power absorbed? For a value of RL. So naturally, ddRL of PL. That is what you would do. So in order to do that, and this is your standard rule for the differentiation, U by V. Okay. So just substituting that here, you would get this kind of a relation. And if you equate that, naturally the denominator is a positive, so you're not bothered about that. So the condition would come from the numerator. And if you just solve for this one, Rs plus RL, you can take that off. So, and if you solve this one, so it comes out as Rs is equal to RL, which is where you got that previous statement from. And further on, I would like you people to check up, if you did a second derivative of this one, d2PL by drL square. It's a maximum power theorem. So you expect that this particular derivative should come out to be negative if you substitute Rs is equal to RL. So please check that out for yourselves. It's an easy check, but do it, so that's a good thing that you've ensured that. Please note that when you have the two extreme conditions, either a short circuit or an open circuit, you have minimum power dropped across the load. Physically, what's happening? If you have a short here, okay? If you have a short here, naturally your VL is 0. So VL into IL 0. If you have an open here, your IL is 0. So VL into IL is again 0. Okay? So the power profile actually drops down to. So this is how the power profile shifts. And this would be the maxima. PL max. This would be PL. Okay. And this would be RL equal to RS. This would be the RL profile. So this would be the standard characteristics actually. You can just check it out. You have this relation for PL. Take any value of VS, take any value of RS, and keep on changing the value of RL. You can either do it in a simulation software or just do it by hand for some particular values, and you can check that this is how this changes. Okay. Now, yeah. Next up, you've got the two, these are again two important theorems, the Thevenin's theorem and the Norton's theorem. Let me just kind of shift this down one little bit so as to fit the voltage. Yeah. Yes. So if you've got this, so the Thevenin's theorem, if you read it overall, don't worry, reading it looks so much. I will still read it out so that you have one. We'll come back to the reading once again after we start looking at the examples. Next one up, there are the examples. So given any linear circuit, rearrange it in the form of two networks. So you are rearranging it in the form of two networks, A and B. Okay. So you rearrange it in that form, that are connected together by two resistance-less conductors. As if they are connected by two resistance-less conductors, you don't have any drop or anything across those two networks. So you're just bifurcating the linear circuit into two parts. One is the supply part, whatever it is, and this would be the load part, whatever that would be. As if either network contains a dependent source, either the part A or the part B, the control variable for that dependent source must belong to that same part. It might belong also to the second part, but it must belong to the same part. Supposing there's a dependent source in A, its control variable should also be in A. Same for B. Define an open circuit voltage, VOC. Naturally, it appears across the terminals of A, open circuit, if B were disconnected. As if you have an open circuit at the terminal of B. Terminals of B, okay? They're disconnected. So that no current is drawn from A. Open circuit. Hence, you cannot draw any current from A. Then, all the currents and voltages in B will remain unchanged if A is killed. That is, all the independent voltage sources are shorted and the current sources are open, and an independent voltage source VOC, this VOC, is connected in proper polarity in series with the dead A network. Whatever is the dead A network, meaning the equivalent resistance or the equivalent, further on, the equivalent impedance of the A part of the network. Okay. Norton's theorem is actually a dual of the Thevenin's theorem. This is for open circuit voltage. This is for short circuit current. Naturally, in place of disconnecting this one so that no current is drawn, you would short it so that no voltage is provided. Okay, so short it so that no voltage is provided, and the equivalent representation would be current source I of SC, the short circuit current source, connected not in series but in parallel with the dead A network. So that would be the dual of this one. So this is the whole theoretical part of description of this one. So let's see what actually is happening. Take a simple circuit first. The objective is, so this is the A part and that is the B part. Okay, let me mark out A and B. So as per what we've said there, so say this is the A part and say this is the B part. Okay, and so we are assuming that these are connected by two resistance-less conductors, as if you could just snap them together. No resistance at these points. Okay, so that's the understanding. So that being so, now Thevenin's theorem, in other texts you will find that we quite often talk about a looking back source and a looking back resistance. Okay, and if you look at this is nothing but that source transformation example that we had worked out. Okay, so that is from that, what does that load view this equivalently as? Thevenin says that we want to view it, as a voltage source, open circuit voltage source, and a Thevenin resistance that is connected to that B part. So this was the B part, as if that would be connected to just a effective open circuit voltage source with an effective series resistance. That is all this needs to know, an equivalent source representation. So the whole objective of Thevenin is to look back from this load resistance and find out this effective source or the equivalent source. So in this particular case, you've got this one. So, and when you're applying Thevenin's voltage, so you're looking at the Thevenin, so you're looking at the drop at this point. Okay, so this is your V of OC. You're trying to evaluate this would be of V of OC. Okay, and so you would find out what is the voltage drop here. Voltage drop here across these 2 points is the same as the voltage drop across these 2 points. This one is open, so no current passing through here. Okay, and I need to mark out plus and minus. The polarity is important. Yeah, so that would be the same as the voltage drop across these 2 points. And what is the voltage drop across these 2 points? 6 by 9 of 12. So that is 8 volts. Okay. Thereafter, you need to know the dead A network, what is the equivalent resistance, looking back resistance, as it is said in some texts. Okay. So you would kill this independent source. Please remember, you can only kill independent sources. Kill this, that means short it. Okay. And looking back from this one, when you're looking back from this end, what are you seeing? You are actually seeing a 7 ohms, then a parallel combination of 6 and 3 ohms. So parallel combination of 6 and 3 ohms, because this is shorted. This is as if shorted. Right. So this 7 ohms parallel with 3 and 6 ohms. This is 2 ohms. So 2 and 7 ohms, that is a 9 ohms. So in this particular case, your VOC would be equal to 8 volts and this R Thevenin would be equal to 9 ohms. Okay?
Okay, ma'am.
And so I'll just revisit this part again. So two networks A and B, we broke it up into that. A and B, connected by conductorless, resistance-less conductors. So that was that. Furthermore, we don't have any dependent source here, so can't illustrate that. We defined a VOC, open circuit, across terminals of A if B were disconnected, so that no current pass. So we open circuited this one. So that is the open circuit voltage that we are looking at. And we needed to look at the resistance of the dead A network. Okay, this one is this, and proper polarity. So VOC is connected with proper polarity in series with the dead A network or the inactive A network. Okay. Now, restriction for the Thevenin's or the Norton's theorems. Linear circuit must be linear. You can't apply it for non-linear circuits. And you naturally only then can you break it up into an A and B components. And dependent source in A must have the control variable in A. I've already talked about this dual. I've already talked about earlier. So the relation for the dual part, this actually becomes quite effective in certain cases. We'll see examples. Sorry for kind of not being careful about having these straight lines out, right? So this is the particular relation that we will be using. So ISC is from the Norton's theorem, VOC is from the Thevenin's theorem, and R Thevenin is the same as R Norton's. That RSI is equal to RSV as we saw in the source transformation or equivalent sources. Okay, so that is, we typically denote it as the R Thevenin itself. In case you have circuits with dependent sources, why are we talking about this one? Because in case we have circuits with dependent sources, then what we do is we can evaluate these two independently, this one, and then effectively find out RTH. RTH would be nothing but this by this. Okay. We will have an example coming up for this one later. Let's just first go through this one. So in this particular circuit, we are interested in this one is your RL. This is the RL. Okay. So as if these are the points for we are breaking the circuit up across this point. Okay. Right. So you're as if breaking up the circuit across this point. So this is your A and that's the B part. Thevenin equivalent. So we are interested in the open circuit voltage across this point, across these two. So V of OC, here we are applying superposition. So due to the 4 volts, due to the 2 milliamperes, the two open voltages or open circuit voltages. So if you've got this one killed, that means this is open. So naturally, it's the same 4 volt which is appearing across this also. No closed path. So that will be 4 volts itself. For the second part, the 2 milliamperes thing. So 2 milliamperes, this would be shorted. So the whole, you would have a current. This would be shorted. This is open. Okay. So that means the voltage drop across this 2 point is nothing but the voltage drop across this 2 point. That is nothing but the voltage driven through this part. So 2 milliamperes into 2 kilo ohms. So 2 milliamperes into 2 kilo ohms. Please remember to use the coefficients properly. Okay, else you will get different values. So it is 4 plus another 4, so that is 8 volts here. Okay, and R Thevenin is for the dead network. Dead network means this is open, this is short. So that means, and you're looking in from this side. You're looking in from this side. This is open and this is shorted, right? So that being so what do you have? You just have 3 kilo ohms plus 2 kilo ohms. So that is 5 kilo ohms. That's your 5 kilo ohms here. So you will draw it out actually, finally you will draw it out as a 5 kilo ohms with a proper polarity. So this would be the 8 volts, and that would be 5 kilo ohms. So this would be the equivalent resistance representation. This would be your RL, or what was that? So you must provide this one, else it is not complete. So the equivalent Thevenin circuit is this. If you are looking at the Norton equivalent means you are looking at short circuit current. That means you are shorting this branch. Okay. If you are shorting this branch, again, currents, short circuit currents due to both of this. So killing this one means you are still opening it. Now you have this source driving the current through this short circuit. So 4 by 5 kilo ohms. So that's your 4 by 5 milliamperes due to this first one. Due to the second one, this is again a short. Okay, this is also a short. So you have current divided in both these branches. So current division. So current through this branch would be nothing but 2 by 2 plus 3, 5 of this 2. So 2 by 5 of this 2 milliamperes, and sum total you would have 1.6 milliamperes. So your equivalent representation would be current source the dead network, please understand, would still be the same. So I'm not recalculating that. So that is a 5 kilo ohms, and this is 1.6 milliampere. Okay, so that is the overall representation that you get. Coming on to another circuit. Now here you've got a dependent source, and where you've got this dependent source, this is V of x by 4000, and this V of x is nothing but the terminal voltage itself. So it is just in Bengali kaner pash diye beriye geche. So you required, let me go back into the definition there. So here it is mentioned, if either network contains a dependent source, its control variable must be in the same network. So network meaning that part A or part B. Okay. So in that sense, it is, yeah, it is there in that A part. This is just the A part which is drawn. And because there is a dependent source, so you can't find a dead network per se. So your option is now to find out both VOC and ISC and interpret R Thevenin or equivalent to R Norton. So interpret the R Thevenin from these two. Okay. Now VOC is nothing but this Vx itself. Please note. This is the terminal voltage that is marked as Vx. That is nothing but the VOC. Okay. So here, if you sum the voltage across the outer loop, and you can do that. This is quite often done, particularly in transistors or op amps, electronic circuits. So if you are summing the voltages across an outer loop, so what do you have? -4 plus of this one. Now, this, what is happening here? This one, there is no path here because this is open. So all of this current will move through this one. So what is the current through this? In this direction, it is minus of Vx by 4000. So what is the drop across this? So -4 plus of 2 into 10 power 3 into minus of Vx by 4000 plus of 3 kilo ohms into 0. There is no current through this. Okay. Plus of Vx is equal to 0. That is your overall KVL through the outer loop. And if you solve from this one, you get Vx is equal to 8. Okay. So you got the Vx. Now the next thing is ISC. ISC means you've got to short Norton's theorem. Norton's theorem means you have to short these two terminals. the moment you short these two terminals, this Vx becomes 0. Because this Vx becomes 0, so this also becomes 0. That means this effectively becomes open. Okay? And since this is open, so your corresponding Ix also becomes open. So what do you have? You have 4 volts itself appearing across this 5 kilo ohms. 4 volts across 5 kilo ohms. There's no circuit current being driven from here. So 4 volts across this 5 kilo ohms. So that much is your short circuit current. So that is 0.8 milliamperes. Naturally, how much is your R Thevenin? This VOC by this ISC, that is 10 kilo ohms. So your equivalent circuit here. So whether depends on whether you want to draw the Thevenins or the Nortons. The Thevenins would be five kilo ohms, and this is 8 volts, and so this will be the Thevenin equivalent, and the Nortons would be the ISC. So this would be 5 kilo ohms again, and this would be your 0.8 milliamps. So this would be the overall response here. If there are questions, feel free to raise them, but I'm continuing on because there's still 2 more, I think, examples that I want to work out. Yeah. This is the circuit for an op-amp, operational amplifier. It's a basic circuit for if you just type in op-amp and search in Wikipedia, you will find this details of this one, or you might be aware of it, some of you. So in the op-amp, this is a typical representation of that. So supposing this is the particular circuit, again there's a dependent voltage source here. Dependent, the controlling variable Vi, this is the differential voltage that appears in the circuit. So this is an open point here. Now again, you have to find out this is the load part of it. So we are looking at essentially this one as the VL. Okay, so this is what we are looking at. Now, when we are looking at this one, so we've open circuited this one, first round. We are finding out VLOC, open circuit. So open circuited this one. Naturally, there is no current path in either direction. This is open as well as this is open. So what is this voltage? This voltage drop is no current through this. So this voltage drop is nothing but this voltage drop in reverse. This is the minus terminal here. So it is minus of 10 power 4 Vi. So VLOC is nothing but minus of 10 power 4 Vi. Furthermore, what you have is, if you write out the equation from here, okay, this terminal outer loop again. So this is minus 5 minus of Vi, okay, plus of VLOC is equal to 0. Just rearrange it, you will get this. Solve these two and you'll end up with a VLOC which is practically 5 volts itself. So this open circuit voltage is almost the same as the supply voltage here. ILSC. ILSC means
why was there no current through the 2 kilo ohm resistor?
You've open circuited this. So what is your equivalent now? This part does not exist. How can I show that? How do I show that? Let me just try and see if I can kind of illustrate to you what's happening.
But 2 kilo ohm is in the inner loop, right? So current won't be there.
Wait, I'll just show you. Should be able to show you. What's happening? Oh, highlight doesn't work on this. Okay.
It doesn't work.
Wait, when I've got through all of this, I'll take up a little extra time for you, but let me do it because otherwise. So this is no longer there. This is open circuited out. Okay. So now, where is your current path? Where will it go? Shuddha Shattva.
Ma'am, there is a loop in the left-hand side, right?
Where is this loop? This is open.
Oh, okay, this is open. Okay.
Okay. Fine.
Okay, ma'am. Yes, ma'am.
Yeah. Now let me undo this one.
So no current is passing through the circuit at all
Yes.
because it is open and even the other loop is open.
Yes. Actually, he missed out on this one that this is open. Okay. That happens because, which is why I kind of illustrated it, just so you get it clear. Yeah. So now it's clear as to what happened till this point. Okay.
Yes, ma'am.
Now, for the ILSC, for the short circuit current. So now we are shorting this one. If we are shorting this one, naturally we've got a current path here. Okay. But what we are what we are writing for that one is this, and the short circuit current is nothing but the ILSC. So it is plus of 10 to the power 4 VI plus of ILSC is passing through this whole of this 2 kilo ohms. So 10 to the power 4 VI plus of 2000 ILSC is equal to 0. Right? This whole of this ISC is, this is a loop. It's still open here. So the whole of this current is passing just through this one. Okay till this? Please give
Yes,
me
ma'am.
yeses or no's so I can proceed on. Okay. And further on, what we do is we write the KVL across the perimeter. If you write the KVL across the perimeter, then what happens is you've got -5 minus of VI. Okay. And because it's shorted, so this VL is equal to 0. So -5 minus VI is equal to 0. Okay. Is this okay?
Yes, ma'am.
This one became 0 because you're talking of a short here now. So you just solve using these three relations, and using that you these two relations. So using these two relations you can substitute.
Can you explain once again?
Yeah, sure. So in the shorting of it, what's happening is we are actually shorting this particular path. Right? So what happened is we now have this as a loop.
Yes,
Okay?
ma'am.
I presume it's Anindita speaking.
Yes, ma'am.
Yeah. So you have this particular loop. So if it's this particular loop, what is the KVL there? 10 to the power 4 VI plus twice of what is the current? ILSC is the short circuit current. 2 kilo ohms.
Yes,
So
ma'am. Yes, ma'am.
this is equal to 0. Done? Okay. Next is what is, since it is a short circuit, so what is the value of VLSC?
It will be 0.
Is 0. Okay. Now if I write the KVL across this perimeter, around the perimeter. So what do we have now? Minus of 5, minus of VI, plus of VL, this is 0, is equal to 0.
Yes, ma'am. Yes, ma'am.
So you've got this one. So you've got this equation and you've got this equation.
We are substituting VI. Yes.
And you get the ILSC as 25 amps. Correspondingly, you can get the RTH as this VLOC by this ILSC, and you will get 0.2 ohms. Okay. Then you've again got to, please remember, you should draw these two, otherwise it's not a full representation. As far as getting marks go, it has to end finally at a Thevenin's equivalent or a Norton equivalent, whatever is asked for. Okay, so you must provide that. Coming on to the other example, this is another case. Now look at this particular example. You've got a 1.5 I dependent voltage source, and this variable I is nothing but the current in this one. Again, so this forms a part of this side of the network, the A part of the network. But what happens is there is no independent source, current or voltage, but there is a dependent source. So how do you really handle it? You cannot have an independent VOC or an ISC because there is no independent value. So VOC or ISC, you know, are going to be 0. But you still have to find out the equivalent looking back resistance, the RThevenin. Due to the presence of this one, you cannot assume that it is going to be a simple parallel combination of these two. You can't. So how do you go about it? One way is that as if you connect, since I'm driving a current through this one, you connect a current source here. Equivalently, you could have connected a voltage source here and looked at the voltage equivalently. So you could have done that also. Okay. So supposing you connect a current source here, and since our objective in connecting this is to be able to evaluate the equivalent look-in resistance, so keep it at a simple value. Simplest value is 1. Okay, so that your RThevenin then works out to be whatever is the terminal voltage that comes out, V, by this current, I. VOC, this would effectively work out as a VOC by the effective current that is supplied out, that is I. This would be effectively the short circuit current. Equivalently, if you used a, say, a voltage source of 1 volt, then it would be as if the voltage source of 1 volt by, you would find out, you would determine the ISC, and so it would be the voltage source by the I, current through this branch. Okay, you could do any of those. Easier is naturally this one because you're dividing by a 1, so it's just directly the value of voltage, whatever you find out. Then what happens? So you apply this one, and easiest is you have this node, take this as reference. So I have this node, and for this node, just write the KCL at this node, and what will you end up with? Yeah, this is the same V because it's as such. So this is the same voltage drop here. So V minus of 1.5 by 3 plus of V, minus of V by 1. Okay. Sorry, this is the current. Just a minute. Yeah. Let me come into it again fresh. So this is V, and you've got V minus of 1.5 by 3 plus of V by 2, okay, minus of 1 amperes is equal to 0. So this is the particular relation that you have. If you went about it clockwise, so you would write V minus of 1.5 by 3 minus of 1 plus of V by 2 is equal to 0, and then rearrange it to get the same thing. Solve for this one, you will get V is equal to 0.6 volts. And what does that give you as the RThevenin? RThevenin comes out to be 0.6 ohms. Okay. So the Thevenin equivalent now simply becomes a dead network because there is no independent source here.
So in this method, we are not exactly short circuiting or open circuiting anything, right?
Not really. You can't.
Yes, no, okay.
Okay, but you are still utilizing the notion of the open circuit voltage here. You are utilizing the notion of the open circuit voltage because if it's an ideal source, it's as if you've connected an ideal source. So it should be able to, irrespective of the voltage here, it should still be able to supply you an IA, 1A. Okay. So in that sense, if you consider, and another reason is that you need not think of it in that sense because it is a dead network anyway. You know that the whole objective of doing this is in order to find out an equivalent resistance, looking back resistance or the Thevenin resistance. You know that had there been any independent source here, you would have moved forward to find out the open circuit voltage or the short circuit current, right? Say this case or any other cases. You had one independent source and you moved forward. But here, because you have no independent source, so you know that you have only an R Thevenin, nothing else. But how to determine that R Thevenin? In order to do that, this is the system that you're using. Okay? Shuddha Shattu, I believe.
Yes, ma'am.
Yeah. Is this much okay?
Yes, ma'am.
Yeah. So this is about the main theorems, and this is actually the mainstay of circuit theory. All these theorems, the KCL, KVL, nodal analysis, mesh analysis, superposition, equivalent source transformations, maximum power theorem, Thevenin's theorem, Norton's theorem. If you can work them out for different examples, it does. Chapter 2, you've got lots of examples. You already have the soft copy. Still, if you wish to, I can send over this PDF that I had taken directly from the book, scanned of the
Yes,
book.
ma'am. That will be better, ma'am. Please send.
So please work them out. Even if it says SPICE example or whatever, do it by hand. Okay. So these are the different examples which are good examples to work out. So which is why I kept them out. If you can do it in the resistive circuit, you can do it for impedances also. So this is good practice material. Next day, I will move into the inductances, capacitances, and then into RL, RC, and then RLC circuits. That's the way forward next. Okay. Next class is next Thursday. And now, happy Ganesh Chaturthi to you all. Hopefully, you have your second half free.
Thank
Yeah.
you, ma'am.
Thank you so much, ma'am. Thank you so
Same
much.
to you, ma'am.
Yeah. Well, let me go off the record also now. Stop recording. Yeah. Okay. So I'll send off the PDF as well as these two PDFs, as well as, yes, of course.